Right, so let's say we have time here and yt. This is time series. Let's get this done first. And you have this series. You also have this series. Also, you have, let's say, this series, and also last one, this series. Now, in each case, will you be able to tell me, or in all these cases, visible, isn't it? Everyone is able to see this? 4 lines. Which of these are unit root processes? Random walk. Anyone? Random walk process. Anything here? Random walk. You have black line, yellow, red, blue. Sorry? Everything apart from yellow is what? Unit root. Random walk. Okay. So mathematically, what is random walk? White noise is stationary, isn't it? It's opposite of random walk. So yeah. Right. So random walk. The yellow. Let's start with yellow. I'm going to write it yellow because I don't have space here to jot down. Is a process can be described using this equation. Black line. Now you see this is upward drift, so this should be something of this type. And you have red. It must be stationary. So it must be just UT, right? And you have blue, this guy here. These are basically 4 data generating processes, right? And these lines can be expressed using this. That's what exactly we do with unit roots. The question 1 is about trying to figure out what yt is, what sort of path yt follows. Does it follow yellow, black, blue, or the last one, red? So that's what we're looking at in question 1. If you can visualize in your mind, sorry, say it again. Black. Black is this process. Blue is this process. Black is this process with drift. Now, the blue and the black processes are more or less the same. The difference here is that in black you have beta 0. In blue you don't have the beta 0. Beta 0 pushes up. Over time, values will go pushing upward. Or maybe downwards if intercept is negative. I have the positive intercept here, so it's positive here. And do we have beta here? Why? And in econometrics, we always have betas, right? We don't have a regression equation without the beta. This must be something wrong there. But what is the beta here? They should be beta. The word unit root, the unit is 1, isn't it? Unit root, unitary value. So the beta 1 here is 1. So this is this is pure random walk, sorry. It's a random walk, unit root process. This is also unit root process, but with beta 0. That's because, black goes upwards all the time. Stationary process doesn't have the YTs. It may have, if you difference it, obviously, but it's just a very simple example of white noise process where UT, assumption is that UT will have a 0 mean and sigma U squared, a constant variance. Now this guy here, yellow guy, has the T, makes it always going upward. But around that t, around the deterministic trend. So if I were to fit that a regression for this regression line, it would be around this t line. Well, it's not that comfortable, convenient for me to draw this straight line, but yeah, this would be evolving around this straight line basically. Let me try it from this part. Yeah, this would be my fitted yt here, straight line. And notice that two of them are stationary. Which ones? Red and yellow. The red is certainly stationary. Well, it's trendless. It has a constant mean, which is described by this black line, and the yellow one is stationary only around this trending line, deterministic trend. Yeah, if you difference yt, this guy will fall to this form, will convert to this form. These are more or less the same, except that yt contains this t value. White noise? You? You mean this? This is white noise. It's a stationary process. Well, white noise would have this sort of noise. It's in your lecture notes as well. This would be the proper white noise, but just for demonstration, I just said white noise is equal to yt is equal to ut. It's actually something else with beta less than 1.
What's the difference between black and blue again?
The black and blue is the beta 0, and there is no beta 0 here. And then the beta 1 here is equal to 1.
So call both of them are unit roots.
Both of them are unit root. One with drift, one without drift. Drift is the beta 0. Drift term is beta 0, guys. If you understand this now, what I've just said, question 1 will be very easy. Yeah? Very easy. Okay, should we start now question 1 if you don't have question? Right, no question. We'll start now question 1 then. I don't know if I've missed anything that would help with question 1. It will be in the question 1 then when we solve, if there is anything that I missed. Right, so question 1 says, suppose this guy, this is real GNP in log, yeah? GNP over P. So YT is basically, you don't have to copy this part. This is just for myself. So this is what YT is. And this person regresses change in YT on its own first leg. So this is AR1 process. Actually, this is single. And we have in parentheses. So to test for unit root using ADF's test, what's the first step? Step 1, what is it? No? Step 1 is to calculate t-stat for beta 1. Now, by the way, this is not beta 1, this is some delta. Remember, in the graph, I showed you the process for YT, trending up and down. And now here, the process is delta YT. So we need to go back to your lecture notes and look at, don't look at it, I'll give you. Don't have to download. Remember YT with drift, because there's a drift term. Was this process, right? The black line going up and up. Now this guy is doing this. He's testing if the process, the YT, follows unit root with drift. The hypothesis here in that case is this, unit root hypothesis in this case. Is that beta 1 equal to 1, because then will be unit root, yeah? Beta 1 less than 1. It's one-sided test. This is the case of unit root with drift. This is a case of stationarity. If beta 1 is less than 1, the process comes back to its mean and it crosses down, up and down quite often. But if beta 1 is 1, it would be the case of black line that I drew earlier. However, with 1 being a constant value here, what we usually do is we try to test beta 1 minus 1 equal to 0, right? Not beta 1 equal to 1, usually. And we call this, let's say, delta. Now, to test this hypothesis using a t-test, we do some transformation usually, right, in here. This is exactly in your lecture notes. Yt minus 1. So I subtract yt minus 1 from both sides of this equation. And this guy here is now delta yt, which is the same as this. Yeah, delta yt. Beta 0 remains. And here we have common yt minus 1, so this would be beta 1 minus 1. And if I rewrite this, this thing here is this thing. Delta is this one here, 0.0076. Now, this is the null hypothesis now, new null hypothesis. And this is the proper null hypothesis, yeah, with the zeros as the hypothesized values. And essentially what we have now is a delta is equal to beta 1 minus 1, and if it's equal to 0, obviously beta 1 equal to 1. Indirect result, right? That's what we are testing, whether yt has a unit root or not. If delta is equal to 0, there is a unit root. If not, no. Okay, now you see it's exactly the same. This is a population regression model for this sample regression model. Exactly the same specification, but just hats implying we just estimated using this population regression model. And we are testing now, what we are testing, to give you further intuition, is that whether our yt is this or this. Either this or this. So null hypothesis implies it's this, alternative hypothesis implies this. So when delta is less than 0, this is the stationary process. This thing is stationary process. This thing gives us this line. If you plug in values into yt minus 1, you get this process over time. If you plug in values into this again, but delta is equal to 0, then this process is the case. Case in mind. Is this clear? Because if delta is equal to 0, what you will have is, I'm going back to its origins. If delta is equal to 0, very quickly, then you will have this process, right? Some drift and stochasticity. And if you use the formula for change in yt minus 1, it gives us original formula. This original one here, right here. Yeah, if delta 1 is equal to 0, delta is equal to 0. And beta 1 is usually tested for equality to 1. So that would be the unit root with beta equal to 0. Equal to 1. Or unit root process. So the word statement for hypothesis, null hypothesis is that there's a unit root with drift, and alternative is that there is no unit root. It's stationary for this formulation, for this specification. Okay, does it give you some sort of intuition to what we're doing and what we have covered in lecture? That's exactly what you covered. Now we need to test now whether delta equal to 0 or less than 0 by looking at these numbers here. So t-stat, that was the first step, and we did a digression. So we go back to t-stat. You obviously should continue here, but let me use this space. Would be minus 0.0076 over its standard error, which gives us minus 2.40. Minus 2.40. Now, in a hypothesis testing, we usually compare t-stat or any statistic against the critical value, right? Now, this is because ADF test, we don't use the normal t-table for alpha equal to 5%, 1.96 or 2.58. We don't use it because t-stat with this specification is not normally distributed with, or standard normal, I should say. So what we do is, we go to ADF table, which is in your book, in the chapter 14, I think, it's chapter 14. And it tells us that for alpha equal to 10% value for this T critical is minus 2.57. That's from your table. And for 5% it's minus 3.41. So if it's 5%, T critical is 3.41. Now, decision time, we know that T critical is 2.40, take the absolute value and take the critical values. And which one is greater in absolute terms? T critical in the at the 10% level, right? And at the 5% level, T critical is greater as well. We do not reject the null hypothesis. Sorry? No, we have the critical values and we have the statistic. Yeah. Now you can compare them in absolute terms, or if you want without absolute terms. But absolute terms is more intuitive for me because that's how you do it in normal t-test. Yeah?
So, in the null hypothesis, the delta is 0. Does it mean it's stationary?
No, it's actually, if delta is 0, then yt is coming back to the original point. Remember I showed you. This really should be not stationary because there's a beta 0, so it goes up or down.
So if it's less than, it's...
Sorry, this could be, the change in yt is stationary, but yt itself, you see we have the yt here. Because delta yt is equal to yt minus 1, right?
Yeah.
That's this case.
So it's stationary. So it's...
I put it back onto this side. Now it's not because beta 1 is equal to 1. It's not stationary. This is stationary, this is stationary. This is, change in yt is stationary, but not this. So beta, you can think of beta 1. In that case, if you take it back to this side, you get delta yt, right? Are you with me, guys? If you take this to the left hand side, you get delta 1 yt, because yt minus 1 is delta yt. And you will get the right hand side as it was before.
So we test delta.
We are basically testing delta originally, yes, but delta is equal to beta 1 minus 1.
So what's our original hypothesis? Delta is 0.
Original hypothesis is this, obviously, but because there is 1 involved, not 0 on the right hand side, we transformed the model into this, so that our delta becomes, so coefficient estimate is tested using the usual formulation for hypothesis statements, delta equal to 0. So if you reject the null hypothesis, delta is less than 0, implying beta 1 is less than 0, which means stationary process.
If delta is 0.
Yeah.
And if it's less than 0.
Sorry, if it's less than 0. I'm saying it's less than 0, not equal to 0. If it's less than 0, if delta is less than 0. In other words, if you reject the null hypothesis in favor of alternative, it must be that delta is less than 0. And beta 1 will be less than 1.
So if delta is 0, then it's not stationary.
If delta is 0, beta 1 will be equal to 1. It's unit root. So implicitly, H null is unit root process. There is a unit root in H null. That's what the statement is. And H1 is that it's stationary with drift. That's the statement, worded statement for alternative and H null statement. Is this clear, guys? Guys, look. H1 in both cases, in the original case or in here, is saying there is a unit root. I stated here apparently. And that's the same here, unit root. This is unit root. In other words, beta 1 equal to 1. That's unit root process. And again, beta 1 less than 1 means it's a stationary process. Basically, yt will be a stationary process. Follows a process that's stationary. Clear now? Yeah? So, we now fail to reject the null hypothesis that delta equal to 0, which means there's a unit root. In the process is unit root or random walk with drift because we have the beta 0. Random walk with unit root. With drift, sorry. If you do not include this, it will just be purely random walk, no drift. Okay, we rejected failed to reject the null hypothesis at both levels. What time is it now? Okay. Right, next. If you do not have question, I hope this gives you intuition and everything else. What comes with it? Sorry. So, erase page. We may not be able to do much today, but we'll continue, and if not, then I'll have to record the rest myself. B now. B, but main thing is that you get the point. B. The guy then probably not satisfied with the results. Usually that's the case. You don't get it. I mean, you aren't happy with unit root test, especially with ADF. It confuses things and gets you confused as well. 6t minus and think about what we are doing here. And why we have this change in yt minus 1 term here, and why we have t term here. What is the aim? You know, in unit root test, as you lecture notes say, if you include t, alternative hypothesis is different. Its statement is different. So, what's the hypothesis here, guys? Again, because this is delta yt, not just yt, it involves delta in the alternative hypothesis and the other one. And this implies basically did I put equality in both cases? Yeah, apparently I did. So that's the case, and this implies basically unit root.
So the transformation will be
This says stationary around deterministic trend. Because we included t.
The transformation is always the same.
The same transformation, yeah.
You need to show it.
No, you just need to test, but I'm showing it to you because you need to get the intuition, not memorize it. You need to learn with intuition. This econometrics is not theory, or application, so we need to know what we're doing. Now in this case, what we're testing is basically, I like graphing it because then it gives you the kind of different perspective on what we're doing. We're testing whether our process is this or this. In both cases, this stationarity I mean, in both cases we have stationary series, but one is around the deterministic trend, one is just level stationary. Yeah. So basically, we need to know whether this process is this or this. Which one is it? Whether yt follows it. Now again,
So that's the same stuff, no?
the same stuff. You do step 1, step 2. Step 1 usually. I skipped so much. So step 1 usually calculating t stat on the beta 1, so delta here, with its what's the standard error? 0.23, giving us minus 349. So this is 349, guys. This is minus 349. Be careful here with the trend. Inclusion of trend means you have to look at another table, ADF table, and there is a title saying with trend title. That's a different T critical now. Because you included T. So then you have to go to the table that says with trend. The other one, the other unit root test critical values that we had before are without trend, with drift only. Yeah. So there are 3 tables in ADF statistic that provide ADF statistic. Third one is without intercept, without trend. It's you test for this. Ah, sorry. Yeah, there's no beta 1, no T. You just test for this. No intercept, no trend. Here, there's trend and intercept. In the original one, the one that we did earlier, first one, there's only one drift, right? Beta 0. Only beta 0. Okay, but we don't do this one. In this exercise, it's only the other. Okay, this is 3.49. Now we go to critical values table, and it's available there in your book. T critical at 5% is now minus 3.41. And again, you take the test stat in absolute value, compare it against T critical, and it turns out T critical test stat is greater. It follows that we have to reject null. That's the answer for question B. Reject the null hypothesis. So reject this and go in favor of this, implying that beta 1 is less than 1. Yeah, it's stationary, but around the what? Deterministic trend. So it's this case, guys. It's this case. The YT follows this. Why actually we're doing this unit root tests? What is the significance of it in econometrics? Why wouldn't we just take the test, take the series like in cross-sectional data and then chuck it into regression and run the regression? Well,
You can't do it over time.
sorry?
You can't do it on time.
You can do it on the time, over time. Why?
With cross-section, because you got like different entities. Like one or
Yes, they are, but then why not in the time series data in cross-sectional data we never tested for unit root, did we? We just said, okay, this is a variable, use it. You see these trends in data, and also stochastic trends that are, that are like black line in the early case, in the first case. They aren't, they are basically, if you have 2 stochastic trended variables, they move together upwards. So let me give you what your lecture notes say. Let's say this is my YT, this is my XT. I really shouldn't do this regression. I shouldn't. It turns out that XT basically has an effect on YT because they move together, in the same direction with a positive beta 1. This is spurious, case of spurious regression. This YT is not white noise. It's not stationary. UT, sorry. And at the same time, maybe the trending behavior of these is because of some other third term. So what we do in time series statistics is that you see this is T now, no I. I means they are entities. We have to make sure that they are white noise, both of them, and then regress them. So I should do this test now. So this is change in y, xt plus ut. Then this would be white noise, and in time series, spurious regression is a nonsense regression. The betas here is nonsense beta. It's biased, in other words. You get a random big number, or very small number maybe. It should be when it should be big value, right? So you have to be careful with time. That's why you need to determine where the process is unit root or stationary. Only if it's stationary, you can calculate your AR model, whatever model it is, AR or the AL dynamic autoregressive lag model or any other models in time series. Okay, we reject the null hypothesis, which means we are in favor of alternative hypothesis, which means the process is stationary around the deterministic term. So if you fit a line, it would be this line, and the process is just jumping up and down around this line. Yeah. Now, second thing is we have to determine what sort of model we have to run now. What should we do to get rid of the trend line? I'll come to that later. But C, can you answer the C now? So far, you know what it is now in A, you know what it is now in B. Comment on A and B now. What did we do in A? Did we reject or accept alternative H now? So we failed to reject null, yeah? What's the outcome of it then? Conclusion? What did we say? If you reject the null or fail to reject. So it's a random walk process. Now notice that it's the same data series. This guy then included T and run the regression with delta yt minus 1. By the way, this delta yt minus 1 is included to account for the possible serial correlation.
So you can say there is an implied bias.
Sorry?
There is an implied bias.
No, don't think of that way. I'll come to that. Now we ran this regression now with some changes and included. So this is called augmented Dickey-Fuller test. We augmented it with T and deltas. Now, in the second case, the same series is telling us reject the null. In the first case, it says accept the null or fail to reject the null. Yeah? In the second case, we rejected the null. What's the significance of these two cases?
If you had more regressions, data changes.
Okay.
It becomes from one level to station.
Yeah, it becomes, I mean, in first case, the misspecification, first of all. It turns out it's a process with a trend. And in the first model, we failed to account for the time trend. As a result, ADF thinks the process is unit root because it's upward trending, isn't it? It thinks it's a unit root. And you will be forced to reject the null. Sorry, fail to reject the null and think it's unit root. You shouldn't stop here and further test whether there's a time trend. And it turns out, if you accept, account for time trend, it's actually a stationary process with a time trend.
So is that omitted variable bias?
No, in this case, we don't think about omitted variable. It's a testing stage. It's the when you specify the AR model that you want to run. That will be the case,
So
yeah.
what we did in the first case?
Sorry, say it again?
What thing did you include in the first case?
In the first case, we didn't include time trend. As a result, we ended up accepting the null, essentially, yeah? Basically. But in fact, if you include the T, it turns out it's not a unit root process. It's a stationary process around a some timeline. That's the comparison. It's an answer to C now. Answer to D. D. If you figure out what the process is, you should be able to do this easily when you in your applied econometrics classes, if you plan to do. So this guy now ran this regression model. Now question is, what is different this time? What is different this time than what we had before? So we don't have T, okay?
Take a difference.
Yeah, we're doing the difference, aren't we? So look, this is delta yt minus 1. In the original two models, we had yt minus 1. And this is delta, what was it? Now, what we should understand here is this now. The aim of this question is just to get you understood. And that to change or to transform this process and this process, and also some other unit root process, into red. So this has to be case always into this process. which is stationary process, you have to take the first differences of yt and then run the regression.
Why do we need to do it?
If you find unit root in your tests, in your series, you have to take the first differences so that this becomes this becomes this, and this also becomes this.
What's the point of modes against the station?
Then you can have stationary time series in your regression model. You can do AR models, ARP models, any of them. You can run the ARP model
What's the point?
because you can then predict the values. Otherwise, with these values, your predictions are biased, are not accurate. You have to convert to this, then predict. That's the whole point, obviously. Yeah, that's what you want to do. Yeah. You know, we did predictions before, and we ignored the case of possibility of stationarity and no unit roots. But with unit roots, your predicted values will not be accurate, will certainly be biased. It will have high errors, basically. Sorry, error. The difference between actual and YT. And also, when you do multivariate tests, multivariate VAR model, for example, multivariate examples, or tests or regressions, then you have to have stationary variables because of nonsense cases that I described earlier.
So you take the first one.
Always difference, first difference. Always use deltas if the process are either of these. The time trend will be removed with differencing. The unit root will be removed with differencing, and also this process will be removed into differencing as well. Okay? So that's the case here. This guy basically took the first difference and ran the regression on both sides, and this model is now is the AR1 model, which can be used to predict next period. Okay, next. Question 2. Well, I think you need intuition for doing this before you do the question 2 again. Maybe if you can answer this question, you should be able to do. Why do we care about breaks in time series? If you read the question, it says a researcher wants to test for a break in her AR3 model. So this researcher basically wants to run this AR3 model and is worried about possibility of having a non-constant, having non-constant betas. These betas may not be constant. What is the implication of, well, where does this come from? Non-constantness. When do betas become unstable? When are they not stable? It's univariate case. Guys? Anyone? Any thoughts? No? Okay. Let me look at this now then. Because this is AR3 model, it involves only one line, YT, one series. Do you think this is YT? Do you think if I run AR3 model here and fit a line, let's change the color to black, it most likely does this. Ah, no, that's too much. That's probably too much. Yeah. Maybe it fits the YT hat like this. Do you think that is a good representation of actual YT? It doesn't look like, does it? Because no, look what happens. It's taking this point here as beta 0 hat. But actual beta 0 in population is this one here. And it's possible that if you continue this, this will be another beta 0. So in a sense, what we're doing is, in fact, there are possibility of 3 processes. 1, 2, and third one. It's actually not stable beta because this curve will have a beta similar to the beta here because they are parallel. It's just beta zeros will be different. So beta 0 is not constant. This line here will have a higher gradient than the other two. But this yt is actually one series and requires 3 different OLS estimations. So betas are not stable if that's the case. If that's the case, they are not stable. Does that make sense, guys? When we mean stability of the, sorry? What does it?
When does it happen?
When you have break here and break there.
So this is when beta becomes unstable.
If there is a break, obviously this one line is unable to represent or kind of fit very well into the data. First of all, the beta 0 is different in both cases, and also there is some trend break. The trend, in other words, these betas will be different as well. Not only this, but these betas are unstable as well, if that's the case. So we need to account for these breaks before you. I mean, the special case or very interesting case is the exchange rate between pound and dollars. From fixed exchange to flexible exchange rates movement change in 1970s made the exchange rate go down drastically. Remember? And certainly there are now 2 different patterns. GDP, for example, for USA dips quickly and comes back in 1941 and 1945 period. So it's like GDP was similar to this. Yeah, you have sort of pulse here. I mean, this line fitted very well, but we won't account for this sort of pulse. This is beginning of the war, it's end of the war, and you have 2008 going like this. So these are breaks. You need to account for them in the regressions. But the problem is, it's hard to detect the breaks. These are visible. I gave this example just to explain you what the breaks are and why should we care about breaks. But imagine this process. Where is the break? It could be there. So many possibilities. Maybe they aren't breaks at all. Maybe this is just a simple unit root process, yeah, with drift. And with this line, I could be running a good regression, AR3 model, for example. Yeah, I could be running an AR3 model with this line fitted to it, and it could describe it very well if it's a unit root. So that's why you need the so-called QLR test for break. Because we cannot identify what the break is or where the break is, we let the test tell us the break time. And this guy in the example here is trying to find the break, if there is a break basically, in his AR3 model. Yeah. Okay, let's do that now. When you run the QLR test, what it does is it will rewrite the original model. So I'll just rewrite it in the interest of understanding what we're doing, yeah? And augments this regression model with some deltas. Let's say dummies. Deltas are dummies usually. Delta is a new coefficient estimate for dummy t, dummy 1t, plus, actually this shouldn't really be, but leave it. Let's say delta 1, dummy t times yt minus 1. So this delta is now coefficient for the composite variable here, times, so this is dummy variable, taking 0 up to some tau, 1 otherwise sort of thing. This is 2, yeah? You have to distinguish between the dummy variable delta t, this dt, and yt minus 1. This is product of them, and this is a coefficient for that. So we call this interaction term. This is just the dummy. And third delta 3, I could call it gamma if I want, but anyway. Plus ut now. And this is quant likelihood specification test specification basically. And null hypothesis in this case is that deltas, all of them, these coefficients, equal to 0 jointly, alternatively not H null. Now, in which case, in which of the statements here, alternative or null statement, we are saying there is no break. There is no, the coefficients are stable. Guys, in which of these statements, H null and H1, which one says there is no break? Exactly. H0 says there is no break. In other words, you go back to your original regression, this one here. Don't augment it. We don't need this augmentation if that's the truth case, yeah? If it's alternative, then these deltas are not equal to 1. So we have to run this regression, and it allows us to find the date. This is the process that, this is kind of specification that QLR test does. It runs the test for each t. So it does it over time for each t point. And calculates, remember this was F test, right? Calculates an F statistic, which is different from F statistic that we usually do. This F statistic we call QLR F statistic. And largest of the F statistic at any point gives us the break date. And with that, we know there is a break, and we account for this by re-estimating the equation. And not much time, we won't go further, but let's go to the exercise now. Okay, we'll have to start another page. Now, given that I have the results here, the table, QLR F statistic table, is in chapter 14. There's a page. Half of the page is showing that. QLR test statistic from calculating the is 378, yeah? Thank you. And if you look up this critical value from QLRF stat now, this is F stat. Sorry, F critical, I'm sorry. Yeah, what's the number? Yeah, what's the degrees of freedom?
4.
Yeah, you have 4 restrictions, yeah? Thank you. Would be apparently 3, at the 5% level, 4 or 9. So this is F critical from the table. This is QLR test from testing this restriction using the formula. And it turns out what we do? We fail to reject the null hypothesis of deltas being equal to 0. That is the case of no break. Yeah? If deltas are equal to 0, then we go back to the original model and we run the original model with no problem. In other words, we don't worry about stability of the betas. They are stable. There is no break. Okay. If you don't have any question, see you next week. But come prepared, please.